Hi everyone, we will solve this worksheet which is about partial fraction decompositions and also improper integrals. Okay, it's a quite long worksheet actually. Let's start. So we have this table. Now when you see a term in the denominator as in this form, you will write this. Okay, you will equalize it to this. And if you see something like this, you will write this, you will equalize it to this, and you will find these numerators, okay? And if you see something like this term, you will write a polynomial in the numerator of degree 1. And if you see something like this, according to its number, its power, sorry, we will write this now. Let's start with this one. We will basically divide this one to this polynomial and get this. So when you multiply this term by 3, you will get 3t plus 3, okay? And if you subtract them, you will get that. So we can rewrite this as in this form. Now the given integrand will be this 3 plus this quotient. Then you have this now. You need to compute this. And this is so easy, right? So you get this. So we get that. Now, what do we do now? We will write this one. So in the denominator, we have this polynomial, right? So we will write it as in this form, okay? So we need to find this a and b. First, we multiply this fraction by this, 2y minus 1, and this one by y plus 4. Now what do we have? Here in the numerator, we have 2ay minus a, and here by plus 4, so we have this 4b. Sorry, by plus 4b. So we have this. Now we equalize, their numerators should be the same. Now we equalize y to this numerator. And we see the multiple of y is 1 here, and the multiple of y is 2a plus b, so we have this. And this should be equal to 0 because we have no constant here. So we have this, okay? Now we solve these two equations, as you know, better than me, I guess. So we have a equals to 4/9 and b equals to 1/9. Now we plug these constants into them, okay? So this is then 4/9 over y plus 4 plus 1/9 over 2y minus 1 as in here, okay? So you know how to integrate them. We have this. This is homework. Here's a hint for you. Even if you don't have this hint, you need to solve that. It's so easy. So what about this d? Now we divide again. Here we have x plus 1. Okay, and the remaining part is this 3x minus 4. So how you should know how to divide these polynomials. Here you have some x with degree 3, right? This is the highest degree. So, and you have here x, the highest degree is 2. Then it means you need to multiply by x that to get x to the 3, okay? And when you multiply by x, you get this, you subtract them, you get that. Now you have x squared, which is the highest squared of highest power of this polynomial. So you need to multiply this then by 1 because you have already x squared there, okay? So the idea is this. Now we have this. Then there the given integrand turns out that now we have this integral. We will again find a partial fraction decomposition for that. So we rewrite this one as in this form. Okay, we have x minus 3 times x plus 3. Now what do? We rewrite it as in this form. Okay, and we multiply this one by this one's denominator and that one by this one's denominator and get this. Now we equalize them to that. These numerators, we equalize them and get this system. Okay, and by solving it, we get these constants. Now we plug them into that. Okay, and here we have this one. Sorry, this integral was equal to that here plus this a, and for a we found that where a and b are these constants. So here we have, and the rest is easy. Here we have 3 over 2, and for that we have 5. We can write outside of the integral that 5, and we will have 1 over x minus 3, which is ln of x minus 3, the integral of that from 0 to 1, and similarly we have that. So we get this. Okay. Now this is the integrand we will deal with. So we rewrite it. Here we have s squared, right? We have s squared and s minus 1 squared. Then for s squared, we write these ones. Let me use this. Now for s squared, we write this, okay? And for this part, we write this, okay? Using the table, you can go back there, okay, to check it. Now we multiply this by s times s1 s minus 1 squared, and this by s minus 1 squared, and this by s times s minus 1, and this s squared, okay? So we get this equality. Now the numerators are the same, right? This and this, we equalize them actually here. Now you see that it's hard to compute directly by using the equation system. So let's make it easier. So let's put s equals to 0. What do we have here? On the left, we have always the same constant, 1. And on the right, when s equals to 0, this is 0. When s equals to 0, this and this, these are 0. What about it? We put 0, so we have minus 1 squared, which is 1, so we have b. That means b equals to 1. Similarly, we tried these ones. Okay, if you have something complicated like this, you can try these numbers 0, 1, minus 1. Or if you have more, if you need more, you can try 2. So the least integers. So we try them and get this, this. And from this, we obtain this equation, and by using s equals to minus 1, we get this. So we solve this and this equalities to get a and c. Here we have a and c, okay? Now we can rewrite this one by using a equals to 2, b equals to 1, d equals to 1, and c equals to minus 2, okay? Now the integrand turns out that, so here we have something similar then, as in here. The only thing you need to do is to integrate, which is so easy, so we have this. This is also homework. So for that, you know how to write. For this one, you will write a over x minus 2 plus b over x minus 2 squared, right? So for this one, we will first make a substitution, then we will use maybe if we need partial fraction decomposition. So we say u to be equal to that, and differentiate it and get this, then 2u du is equal to dx. Note that u squared is this, then it gives u squared minus 3 is equal to x. Now we're given that, we rewrite it using u and du and get this one, and this equal to 2, right? Because x equals to u squared minus 3. So what do we have? We have this. Now this integrand needs to be decomposed. So we will use the same table to obtain a decomposition. We write, this can be written as, actually its factors are u plus 3 and u minus 1, so we can decompose it by this. Now we have this one, this fraction. Now 2u equals to that, so a plus b equals to 2, and as there is no constant here, the remaining part will be equal to 0. So a and b are these ones, okay? So here we had this. Now it turns out this this decomposition. So we have this one now, okay? And you know how to integrate it. It's easy. You need to obtain something in terms of x, right? As it's the given integral. So you need to write instead of u square root of x plus 3. Don't forget that. So here we have the result. And this is also homework. Now we're given this one. We will use this substitution, okay? So it gives us u to the 6 equals to x, okay, and differentiate it and get this one. And square root of x is, so here we use this equality, square root of x is equal to u to the 6 to the power 1 over 2, so we get u to the 3. And similarly, we obtain this one's function in terms of u again. So this is equal to this integral, okay? And instead of dx, we write 6u to the 5 du, as in here. And we know square root of x is equal to this, and this equality we have already there. So we have this. Now what do? We will compute this by using this polynomial, the dividing the polynomials. Here we have, okay, we rewrite this. If we write denominator in terms of, in the parentheses of u squared, we get, and if we simplify u squared, we will get 6 over u minus 1. So here we have the result, okay, we have this. The integrals are easy, you know how to integrate it, okay? So first we divide them, okay? Then we rewrite this one here, okay? After substitution, of course. We write this one and we know how to integrate it, so it's this. Okay, we will determine if the given integral is convergent or divergent. If there exists a limit in real numbers, okay, we say it's convergent. If the limit is infinite plus minus infinity, we say it's divergent. So you need to know these recalls, okay? I will make in a few seconds. So first one is this. This is a definition of an improper integral. We say it's type 1, okay? If some if the given integral is in this form, you can compute this one to determine if it's convergent or divergent. Okay, so in the above boundary is not a constant but infinity. So using this one, okay, here we have an integral. The boundaries are a and t. First you compute this integral, then you take the limit where t is approaching infinity. Okay, at the end you will obtain this. Actually, it's the idea is this. So for example, you have some function, for example, something like this. Okay, suppose it's tangent to this x-axis. Okay, so we were computing before the definite integrals. We had boundaries before, a and b, something like this. Okay, if we say this is f of x, we were computing f of x dx between these boundaries. Okay, now what do we do? For example, for this part, the above boundary is not b. There is no boundary above. Okay, so instead of this b, we don't have b now. Okay, now what do we do? We write infinity. It means we compute all areas, okay, till infinity. Okay, but starting with a here. So it makes sense that then, right? If we write t there, so for t, okay, we first find this area, then if t is approaching infinity, we will get all areas till infinity, right? Okay, so the idea is this. Now for this one, this is type 1a, right? Type 1a, okay, because this recall will continue, that's why we have parts. Now what do? We then compute this limit, okay? This was the given integral. We will write, instead of this infinity, we will write t and compute the limit when t is approaching infinity. So what do we have? First, we need to integrate it with these boundaries 0 and t. Here we have the integral, okay, and we integrate it and we get this one, and we evaluate it and get that. Now 2 over 3 is a constant, it doesn't depend on t, so we write it outside of the outside of the limit, sorry. And we have this then. Now when t is approaching infinity, here we have infinity, right? Infinity minus 1 gives infinity. So this limit is gives us infinity, which means this integral is equal to infinity. It means it's divergent, right? As we don't have some real number here, it's divergent. Now we have these definitions, so you can stop the video and note them if you want. Okay, so here we have another one. We will see in a few seconds the exercises, so we will use them. Now we have this integral. This is type 1c. Let's look at that together. It's this, okay? If we know these integrals, both of these integrals are convergent, then we define this integral from minus infinity to infinity. We have this sum then, okay? But they should be convergent for any a, for any real number, okay? Because we want to compute on all real line, okay? That's why for any a, they should be convergent. Now let's look at that. Okay, so we have this this integral now, right? Now we pick for a 0. Okay, we pick 0. And we divide this integral with these two integrals. Okay. Now we call the first one 1 or I sub 1. Okay. And this one I sub 2. Let's compute this first one. Now here we have this integral. Okay, from minus infinity to 0. This is type 1b. You can go back there and check it. So the limit of this integral when t is approaching infinity, we compute integral first. It's polynomial, too easy. So here we have this one. Now when t is approaching minus infinity, here we get, it's obvious, minus infinity. It means this part is divergent. But this says that if they both convergent, you have this. If they both convergent for any a, but we pick a equals to 0 and we solve that one of them is not convergent, it means this given integral is not convergent. Okay, we conclude it. So this is divergent. Okay. Now we're given this one. So what do we do? If we first rewrite this denominator, okay? Now by using this partial fraction decomposition, you should compute by yourself that we have this one, okay? We can write this 1 over 4 outside of the integral. Now we have from 2 to infinity, it's type 1a as we did before. So we compute this limit, okay? When t is approaching infinity, we compute this limit. So here we have this integral, we compute it and get, here we have ln something minus ln something, so we can write it as this fraction. Now we evaluate it and get this one. The logarithmic function is continuous, that's why we can replace this ln and limit, okay, as in this form. If the function is not continuous, then you cannot do this, okay? So here we have. Now this one's limit is actually 1, it's obvious. So we have ln of 1 minus da da da. Ln of 1 is equal to 0, so we have this one. It's some constant, it's a real number. So it means this given integral, okay, here we have, is convergent. Now we're given this one. So we need to check the recall again. Here we have. So if some integral with these boundaries a and b, if it's continuous on this interval and this continues at some point, okay, b, here we have open interval, okay. So if it's discontinuous at b, then we check this limit. If it exists, then we write, we equalize it to this limit, okay. For this one, it's again the same. We check this limit, okay. So why do we approach a from right hand side? Because it's open here and f is defined on this interval, so we need to approach a from right, okay. The same situation, similar situation is holding here. So if f has a discontinuity at c, where c is in between a and b, and both these integrals are convergent, then we can write this, okay. But it's not enough to have some point on which f is not continuous, but these two integrals should be convergent too, okay. So let's check that. Okay, So the function is here 1 over square root of 3 minus x. And it's obvious that it's not defined on 3 because denominator will be 0. So it's not continuous at x equals to 3. Okay. So let's evaluate this then. Okay, because it's defined on this interval, right? The boundaries are 2 and 3. So here we have, and it's not continuous on 3, so we write as open. Now we're approaching 3 from left hand side, so we have this limit now. We compute this integral and get this and get this. When we put t equals 3 and get 0 there, okay, so we get 2 as the limit. It's not infinity or minus infinity, so it is convergent. It means this integral is convergent to 2, okay? Now for this one, it's clear that this is not defined on 2, right? So here we have 2 is in this boundary, right? 0 and 5. So by the recall, we can write in this form. Now by partial fraction decomposition, we can rewrite it as in this form for the first part, okay? Now it is, remember, equal to this limit from left hand side. We need to approach 2. So here we have this. Now we compute it and get that one from 0 to t. And here we have this one. When we put 2 equals to t, here we have minus infinity by the logarithmic function. Now, then we get minus infinity. It means this part is not convergent. It means this is not convergent either. So it's a divergent integral. Now we will use the comparison theorem, okay? Now it says if you have two functions of this form with this condition, where x is greater than a, then this integral is convergent. If this is convergent, then so is this integral, okay? It's actually, you don't need to memorize anything actually, because you can visualize it as in this form. So here we have, let's call A, okay? Now, so this is F, and let's have G, okay? So G should be either equal to F or less than F. So let's, G should be something like this, okay? So when we compute the area, okay, the integral of f, it says it's convergent. It means the limit of this area is finite. And we see that the limit of the area below G is less than, should be less than f, right? The area of f, right? Because it's less than f. So if this is, the bigger one is convergent, then the less one should be already convergent, right? So it means that, okay? This means that. And it says if this is divergent, so the less one, okay, the less one is divergent, then the bigger one should already divergent, okay? So it says that. Now we have another theorem which says this. If you're given this integral, and if p is greater than 1, then this integral is convergent. Otherwise, which is this situation, it's divergent. We will use that too by comparison somethings. So here we have this function. This is obviously bigger than this one 2 over x, because e to the minus x is greater than 0, because e is something greater than 0. So we have this inequality. Now 2 over x is greater than 0 when x is greater than 1, right? Then we have this. So we have, our candidates are, now this is candidate for f of x, and this is for g of x. They are both, they satisfy that property in the comparison theorem, and they are greater than 0. Okay, so here we have this integral. We know it's divergent because here we have p equals to 1. Okay, so this integral is greater than that, and it's equal to 2 times this one, and this is divergent. Now, if we apply comparison theorem, we get this is divergent too. Okay, this is homework. Now this is the last question. So here we have this integral. We know sine squared is always less than 1. Here we have the inequality. It's always true for any x in the real numbers. So this is less than 1 over square root of x then. Now we compute this one. So its integral is this limit when t is approaching 0 from the right hand side. Why 0? Because in the denominator x cannot be 0. Okay, it's discontinuous at that, as in this type, sorry. So here we compute it and get something, some constant, some real number. So it means this is convergent, and this is less than that. By comparison theorem, we get this is convergent. Okay, so this was the last question. As I said before, you can attempt the office hour if you have any question. So see you there.